Hello everyone. This video will be on the 3.15 section of the IBAA curriculum. Please pause the video for a second to look at the concepts and contents for this section. There are no formulae. One sentence that summarizes this section is, two lines can be related in multiple ways. So in the last video, we looked at some properties of lines and how to express them using equations. In this video, we will bring two lines together and see what we can do with them. Let's first use a 2D version to look at some behaviors. First, two lines can be intersecting. A typical example, right? Two lines intersect if they're non-parallel, and they form a point of intersection, or have one unique solution, and there's an angle between two lines. Next, two lines could be parallel. Two lines are parallel when the lines have the same gradient but different points, and there are no points of intersection or no solutions. Lastly, two lines could be coincident, when two lines have the same gradient and the same position. There is an infinite number of points of intersection or solutions. Now, these are in a 2D setting, and they're all possible in 3D. However, there is one more type in 3D where two lines are skew. The lines are skew when they're non-parallel and thus different direction vectors, yet do not have points of intersection or solutions. Imagine you're holding two drumsticks and that the sticks are hovering over each other at a different angle. Then the drumsticks are skewed to each other. You can see some kind of distance between them. Now, when I was explaining these relationships of lines, I told you about solutions. But we have to know that solution of two lines is equivalent to the point of intersection. And from the number of solutions, we can deduce the relationship between the two lines. Now let's look at an example where, let's say line 1 is given as 3, 2, 1 plus lambda 1, 0, 2, and then line 2 is given as 1, 0, 3 plus mu 3, 2, 0. Then we can use the equation to find the point of intersection. And let's use the parametric form to solve this. So my first line will be 3 plus lambda, x equals 3 plus lambda, y equals 2, and z equals 1 plus 2 lambda. Line 2, x equals 1 plus 3 mu, y equals 2 mu, and z equals 3. And if I'm looking for the point of intersections, then I know that x and y and z values should all be the same, right? So I know that I have 3 plus lambda equals 1 plus 3 mu, 2 equals 2 mu, and 1 plus 2 lambda is equal to 3. And I know the answers are quite obvious, but let's use the systematic way to find this. What we're going to do is we're going to move all the lambdas and mu's on the left-hand side and move all the numbers on the right-hand side. So it'll be lambda minus 3 mu equals negative 2, and negative 2 mu equals 2, and 2 lambda is equal to 2. From this, we can see that, the lines are coincident when the lambda equals to 1 and mu equals to 1 as well. So now we know the lambda and mu, we can substitute our lines with the known lambda and mu to find the point of intersection. So for line 1, it becomes 3, 2, 1 plus 1, 0, 2, which gives us 4, 2, and 3. For line 2, we get 1, 0, 3 plus 3, 2, 0, and we also get 4, 2, and 3. So we know that two lines intersect at the point 4, 2, 3. The angles are a bit easier. We simply take the direction vectors of the line and find the angle by using the formula, the angle between two vectors. So I'm going to do the angle between two direction vectors. I'm going to use the formula from the section 3.13. Cos theta equals v1 w. So scalar product of the two vectors divided by the magnitude of each vector. I'm going to go cos theta equals, and I'm looking for the direction vectors, right? So it'll be 1 times 3, 3 plus 0 divided by 1 plus 4 square root 5 and square root of 9 plus 4, 13. It'll be 3 over square root of 65. I know that theta has to be the arc cos of 3 over root 65. Let's try another example now with L1 with the same value of L1, and this time L2 will be different. Let's try L2 this time as 4, 2, 3, and plus mu -2, O, and -4. And let's do the same thing. So I'm going to change this into the parametric form. X equals 4 minus 2 mu, y equals 2, and z equals 3 minus 4 mu. So if I bring the equation from above, I know that same thing. I want that x and y and that to be equal. So 3 plus lambda equals 4 minus 2 mu, 2 equals 2, 1 plus 2 lambda equals 3 minus 4 mu. And let's do the same thing, put everything on the left-hand side, lambda plus 2 mu equals 1, 2 equals 2, it's trivial, so I'm not going to write that. I'll assign 2 lambda plus 4 mu equals 2. What do you notice from here? And when we simplify the equations, all the equations become the same. We only have one equation left because the second equation here, again, if I divide the coefficients by 2, it just becomes lambda plus 2 mu equals 1, which is the same as the first equation. This time we cannot use the system equations, and at this point we notice that for any value of lambda and mu, that the equations are always true. Therefore, this means that there are infinite number of solutions. What does that mean? Well, that means that the two lines are coincident. Lastly, let's go with the final example. This time L2 will be -2, 5, 2 plus mu, -2, O, and -4. Let's again try to find the point of intersection. So this time again, x equals -2 minus mu, y equals 5, z equals 2 minus 4. Again, we'll use the same. Then it becomes 3 plus lambda equals -2 minus mu, 2 equals 5, 1 plus 2 lambda equals 2 minus 4 mu. So right off the bat, if you look at the second equation, you can see that this equation is not true. AKA, there's no values of lambda or mu that suffices the equations to be the same. And if there's no values where the equations are same, which means that there are no solutions. And if there are no solutions, we know that the lines are either parallel to each other or skew. And we can see by looking at the direction vectors, the direction vector of the first line was 1, 0, 2, and the direction vector for the second line was -2, 0, and -4. We can see because the one direction vector is a multiple of the other one, we know that the two lines are parallel to each other. If I had one change, for example, my second line on the last question was -2, 0, and -6, then this equation would have still not worked. And because the direction vectors are not multiple of each other, then these two lines have to be skew. Right. So I think we can try to go a bit deeper into this topic. And this time we're going to try to find the distance between the two lines that are either skew or parallel. This is extremely difficult, but a very juicy part. So pay attention to this, okay? So let's use an example from above to find the shortest distance between the lines. Well, so if I visualize the two lines, well, the shortest distance between the two lines have to be their perpendicular distance to both lines. So we know that this little line has to be perpendicular to both of the lines, line 1 and line 2. Well, what is that vector that describes the behavior? Well, because we're looking for a vector that is perpendicular to both lines, then we want to find the vector product of the two direction vectors, and it will give a vector that is perpendicular to both lines. Then we can imagine two planes that are parallel to each other with the normal vector as the vector product of the two direction vectors of the lines, but one contains L1 and the other contains L2. So if this line is L1 and if this line is L2, then we can have one plane here, and we can have one plane, the second plane like this, and they should be parallel to each other. Then the matter of finding the distance between the two lines becomes the matter of finding the distance between the two planes. First, we can try to, if we have a point P here and a point Q here, what we can do is we can try to find the vector PQ, and then what we'll do, we're going to project this vector onto the normal vector here. We're going to call that n. Okay, what it does is if I see this from the side point, now this normal vector is like that, and then that's my PQ vector. So if I do the projection, I can just move my normal vector on the foot of the Q. I can just project it. Okay, so if this vector, if this angle is theta, then we can say, oh, the length of n is same as the length of PQ cos theta. And how do you find the cos theta? Well, the cos theta, we know that from the formula booklet, the angle between the two vectors. So we can find the scalar product of PQ and the normal vector, and then we divide it by the magnitude of PQ and the magnitude of normal vector. Let's do that. This time will be magnitude of PQ times the PQ scalar product with the normal vector divided by magnitude of PQ and magnitude of normal vector. And we know that because these are two cancelled, we know that PQ and is equal to normal vector like that. so we can find the distance between the two lines like this. I understand that the last part may be extremely difficult to get it, but this is just so you know that such methods exist. Let's finish the video with a question where we're going to use the same line 1 and line 2. Line 1 is 3, 2, 1 plus lambda 1, 0, 2. And this time line 2 will be 1, 0, 3 plus mu of 1, 0, 2. The two lines are parallel, and can you try to find the distance between the two lines? I hope you enjoyed this video, and try some questions in this section to really master the skills that we have learned. Anyways, I'll see you in the next video. Best wishes.